I'm going to try to cover what is an object today. Traditional storage, you have a SAN, you make a LUN, you have an app pointing to a single LUN. You allocate more spindles to get more performance. Sometimes you make the LUN too large in capacity to get enough spindles for your performance. So it's a personalized workload per LUN. It's one application generally holding a LUN. You isolate to get performance and reliability, and then to scale you isolate further. So maybe this whole tray is dedicated to my Oracle. Maybe this whole array is dedicated to my Oracle. It's not necessarily shared storage, even though it sits in one metal frame. Data is growing tremendously. I think it was Hadoop started the concept of never delete anything. Works very poorly with a traditional isolated workload where you have performance bound to capacity. Object storage, Amazon S3 was mentioned earlier. I think they're the first to make this a real product for the masses, right? It's content addressable storage has been there before, but S3 brought it to a bigger world. On your right, there's a cloud around your spindles. That's what object storage backends look like. That's what Swift looks like. Take a bunch of hard drives, and with software, you glue them together. You point your applications directly at the storage. So instead of having servers mounting your storage, your applications talk storage now. Software as a service apps, mobile devices. Nothing stops your cell phone from talking to Swift directly. Large file, big data applications, your web servers, your end user Internet Explorers talks directly to Swift. Uploads, downloads, it doesn't matter, right? It's persistent storage and works really well with cloud where you don't necessarily have persistent compute instances. Move your persistent storage out to Swift and it will live there long after the compute instances are gone. I mentioned S3. Hopefully everyone knows what Amazon S3 is. Rackspace Cloud Files is another public provider of object storage. HP has a cloud object storage in the Helion product. They also have an on-site cloud object storage for private clouds. IBM purchased SoftLayer. They have an object storage offering. I think there's 100 more companies to mention. So the common thing here, so at the bottom, right, OpenStack object storage system, which was written by Rackspace originally, before OpenStack, to compete with S3. They had a previous product that did not scale anymore. They rewrote it with the same access interface. It became Swift. Together with NASA, they made OpenStack. HP's Cloud Object, IBM SoftLayer, Rackspace, all running Swift in the backend. Swiftstack, we have a product for how to manage Swift in your enterprise. Swift is an enormously large storage system deployed in hundreds of places with many petabytes of storage behind it. So to come back, what is an object? The picture could be a file. In this case, it's an object. So we say a file plus metadata is an object. So you take your Golden Gate Bridge.jpg, upload it into Swift. Swift will attach metadata to this object by itself, an MD5 checksum, what is in this file, etc. When was the picture taken? Is there a category? Where is it from? It's in a state called California. It's in a city called San Francisco. You can add, remove, modify metadata without ever touching the object itself, the file. If you in 3 months from today have a new tag that you need to start recategorizing your images, go right ahead. You don't have to pull data in or out. What is metadata? It could describe the object, right? Doesn't have to. It could, probably will, otherwise it doesn't make sense. We store it with the object. So in Swift, there's no centralized metadata repository. We use extended file system attributes to store metadata about objects. So it's truly stored and replicated with the object. It can be added, changed, removed independently of any operation to the object itself. And then for indexing, you can index metadata. The way Swift works today, you would index metadata outside of Swift, but there's hooks in the software where that can be put in. Indexing is very application dependent, right? What type of metadata are you using? What do you want to query on? So it's a custom implementation for each use case. How do you access your objects? It's no longer a file system. It's no longer a server mount. HTTP is your access protocol. There's a DNS name somewhere, example.com. So API version is version 1. It still has not been modified or revised since Swift was released, which means that Rackspace knew what they were doing. Right? That was a good API on day 1. Then you have an account. So it's not a user account, it's a storage account, it's a Swift account. Everything is organized in accounts. In accounts, you can put containers. So in the file world of things, think folder. In the Amazon world, think bucket. So in an account, all you can put is containers, and then in each container are the objects. So you can't put objects directly in an account, you can't put a container in a container. That is your URL to access that object. I don't know if you can see this from the back. There are some key concepts to know. Containers are unlimited. They're encouraged for performance, for multi-concurrent access. The more containers you have, the more performant will your system be. Object names can contain a /. So you can mimic an old file structure by putting /s in an object. And it can also be used for container listing, so you can put in a prefix. Show me all objects that starts with folder name / star to show a subset of objects in a container. RESTful HTTP API. You can use regular HTTP verbs to get your data or put your data. So get, put, copy, delete, head, and post. If you're downloading a large object, and while you are downloading the object, if someone else calls a delete on that very object, what happens? I'm sure there's a race condition somewhere. I would think that it will actually not be deleted, because the delete operation itself is not an immediate, it's a tombstone, and an object gets deleted after a tombstone is placed. Because you're downloading an object does not mean that you have a lock on that object and no one else can do anything to it. But I would assume that your download will just fail, right? You might get the first bytes of an object, and then that operation will fail. It's kind of like on your Windows file server, I have a Word document open. Someone else can delete that Word document, and I can't save my document, right? Or someone can put a read-only flag on a Windows file share. Now I can't save my modifications I've done to a document while it's been open. The storage in object storage is application aware, right? So the application has a lot of freedom to do with the storage what it wants. And it's a key concept for a developer using object storage versus using a traditional POSIX file system. And we have a lab this afternoon where we can actually do that. So you can upload a text file, modify it, upload it again, and then go and see all your versions. As an application, you can go back and say, show me all the versions of this object, and you'll get a list of timestamps when those different objects were created. Swift has its own metadata tags that it manages, and there's customer or application-defined metadata on top of it. Why object storage? What is it good at? Why do you use it? It scales to billions of files, single namespace, hundreds of petabytes of data. There are examples, Rackspace being the poster child, right? Their public cloud is hundreds of petabytes, or at least over 100 petabytes as a single namespace, single cluster. Extremely concurrent storage, so you can have endpoints around the world hitting the same storage, hundreds of applications, millions of users accessing the same storage at once, because it scales sideways. There's not a single controller managing the storage behind it. Separation of software from hardware. Swift is a piece of software. It runs on hardware. Use Dave, tell you what hardware you want to use for your use case to make the software performant to what performance levels you need. Durability can provide many nines of availability. There are published reports of Swift clusters in production with 12 nines of availability of your data, right? So traditional storage, 5 nines is awesome, 12 nines for Swift, 1 second per year of downtime, right? Rich metadata, so you don't need to have a transactional database outside of your file system to maintain metadata for your files, or your objects in this case. Geo-clustering, Swift is designed to live around the world. So you don't replicate clusters between data centers or geos. You tell Swift, the software, where are these nodes? Are they close by in one data center, or are they between data centers? And you can truly have a global cluster that's a single namespace that spans the world, and do intelligent replication inside of that cluster, but you don't replicate clusters. It's designed to serve billions of objects, petabytes of data without having downtime. If you host a public cloud, you never have the luxury of having a Saturday night to reboot your systems. In today's corporate worlds, I think we're getting the same place, right? There are very few maintenance windows to take a system down. Comes even more true when you see the previous slide where all applications hits the same storage system. You can never take that storage system down. And Swift provides functionality to never ever go down, even if you do operating system maintenance, hardware maintenance, Swift version updates, it all keeps running. It's all available to your applications.